we are going down. Was 2 years back it was 49. So it's patients at very young age they got diagnosed with breast cancer. So I'm not sure frequency because population size is different. In the United States, 14% from the whole population. We do have 19 point something. So the frequency is high. The age of diagnosis is younger. We do have many young patients who are diagnosed with breast cancer. Could be environmental, could be genetic.
Thank you very much.
Our next speaker is Dr. Maha Habash, and the title of her presentation will be the use of comparative intramolecular contact analysis to build valid pharmacophore models against soluble oxide hydrolase toward development of potential anti-inflammatory agents. Dr. Maha is an assistant professor of medicinal chemistry and drug discovery at Applied Science University. She has her PhD degree from the University of Jordan at 2010, and she has 10 published papers in reputable journals, supervised a number of postgraduate master's students, and she is now the Dean Assistant at Faculty of Pharmacy, Applied Science University. Welcome, and you can start.
Assalamu alaikum. Today I will talk about the use of a novel methodology, which is the comparative intermolecular contact analysis to build valid pharmacophores against the development and the discovery of immuno and anti-inflammatory agents targeting the enzyme which is soluble oxide hydrolase. My talk will be divided into a small introduction about the inflammation, my target, and the brief introduction of the methodology we use, experimental part, and final conclusion. As we all know, the inflammation is a non-specific complex biological response which is against a certain injury or characterized by damaged cells or irritants, and these swellings and redness, heat, and swelling, as we all know, are the major symptoms of inflammation. These signs appeared as a result of a long cascade of arachidonic acid and its sequencing and the conversion to other chenocytes or cyanoids, which are a major cause of the inflammation symptoms. Our target is SEL. Our target is SEH, as you see here, is soluble oxide hydrolase. This enzyme is involved in the last stages of inflammation process. So, as inhibitors, as SE inhibitors, discovery and the use of these inhibitors will improve the pro-inflammatory symptoms and prevent the inflammation progress. As we all know, there are several published papers and a huge number of inhibitors that has been already synthesized and published in several papers against the soluble oxide hydrolase enzyme. Our target was using the already published inhibitors for the discovery of new potent compounds. Using these inhibitors by the structure-based methodology, and the structure-based methodology, as medicinal chemists know, is based on docking process. Docking was made by using the ligand-fast process and a huge number of compounds, which is around 248 structures of several inhibitors that were assayed by the same bioassay method. The concentration of inhibition was expressed by IC50 value, as we all know, and these inhibitors were docked, as I said, using the ligand procedure. Our methodology, which is the novel method, based on distinct and care examination of the contact amino acids in the binding pocket. We all know docking, we all know the binding site, but not all the binding site is essential for interaction with the inhibitors to exert its effect. So the DPC, which is the contact analysis or the contact intermolecular contact analysis with comparative effect, it mainly depends on the study of this contact between our inhibitors and the amino acid at certain distances. First of all, the docking of the groups is scored, as we all know. Then the dot pose or conformer of each ligand is or evaluated to identify the closest atomic neighbors. We choose two distances, which is 2.5 angstrom and 3.5 angstrom to study the contact between our inhibitors and the protein. The result of the step 2 is mainly a matrix of 1 and 0 numbers. If our inhibitor has a contact at this particular atom with this particular amino acid, then the matrix will give us number 1. If not, it will be a 0. This matrix is then each individual column in the resulting matrix in the previous step will be regressed against the bioactivity of these compounds. So we will give the bioactivity of our structures, our inhibitors, as a column in our matrix. Then genetic algorithm will be accommodated and the summation of the columns will be obtained. Finally, our statistical analysis will give us the best results for the choose of the generated models. After examination of several models, our best models were using ligand fit, as I said, in a nice case of my inhibitors in the absence of water molecules, using score 2 as scoring function and at the distance which is 3.5 angstrom. The difference here is between the exclusion volumes. The first model is 5 exclusion volumes, where the second one was the 10 exclusion volumes. These statistical methods was obtained for expression that is the best and the highest models that we get. Finally, the method that we did is using studio to build up our model, our pharmacophore. First of all, we determine the amino acids, whether positive or negative. We determine mainly and exactly the atom that we have the contact with. Best behaving compounds and best potent compounds were aligned in this binding pocket. Finally, our features were put according to the amino acids. So we put donors, hydrogen bond donor, acceptor hydrophobic features according to our inhibitors and according to the contact amino acids aligned with. Final step of pharmacophoric modeling was the addition of the exclusion volumes, as we said. The final pharmacophore that we get, as we see, here we have two hydrophobic features, one hydrogen bond acceptor or 2, and 2 donors. This pharmacophore was validated using group analysis. And you here see the AUC, area under the curve, accuracy, specificity through positive rate and false negative rate of the obtained pharmacophore to ensure its selectivity for the selection of my inhibitors rather than other zinc compounds, if you have an idea about group analysis. The other method, or other model, was built in the same manner, but the difference here is the 10 exclusion volumes, and of course there is a difference in the orientation of the amino acids in the binding pocket. This pharmacophore was fine because its analysis was not as good as the first one, so we do refining to add the exclusion volumes, and the exclusion volume addition improves its rock analysis. This is before refining, and this rock is after refining, and this is the results as numbers of the AUC again, and the accuracy, precision, specificity, and the true positive rate of a false negative rate. Finally, we do the screening against the national cancer compounds. We obtained our compounds and captured hits after in vitro analysis. We isolated our enzymes from liver homogeneate, and we done the highest percentage of inhibition was for these 3 compounds, as you see here, 64% inhibition, 92% inhibition, and 89% inhibition at 10 micromolar concentration of these inhibitors. Our conclusion was that against the ligand fit process or docking that we did, the best conditions that we obtained was in the absence of water, using LibScore 2 as scoring function, and we are these are the optimal docking conditions to obtain new SEH inhibitors. Our future work will concentrate against mainly optimization of these inhibitors and in trial to find new and potent inhibitors, inshallah. Thank you for your listening. Thank you.
Thank you, Dr. Maha. Is there any question? Any question? Okay, I have one. You perform structure-based pharmacopharmacology. You form. Yes. Okay, can you give us brief idea about the ROC analysis?
Yeah. ROC analysis mainly is the aim of it is to distinguish between that your inhibitors are really inhibitors of this drug or not. If your pharmacophore can catch only the inhibitors or any other molecule. So you can add a group of molecules which is known as zinc molecule, if you know, yes, because this, which is mainly zinc, contains a huge number of. Against each inhibitor of your compounds, you add 35 or 36 as you want of zinc or decoy compounds that are very close in structure. So if your pharmacophore can catch your inhibitors against these zinc, this indicates its selectivity. Okay? Yes. Okay?
Thank you
very much. Thank you.
Okay, so we're gonna go next speaker, Dr. Kamal Sridan. He's associate professor at Department of Chemistry, University of Jordan. What I have here, actually, he completed his PhD at age, I'm not gonna say age, although he put that age, from Tübingen University, Germany. He did his doctoral study at same university. And also he did part of his postdoc at Max Planck Institute in Germany. And currently he is associate professor of organic chemistry at the Department of Chemistry at the University of Jordan. He published about 55 papers. And he has one patent and one published book actually. So that's all he has. So for his
Today I will talk about the significance of force degradation and impure profiling in pharmaceutical finished product. I will start with definition for some simple concepts and terms. Impurities, including degradants, they are unwanted chemicals that they are present in the finished product. These sources are from either during the synthesis of the active ingredient or during the formulation of the final product, I mean excipients with raw material, or these impurities could be originated from storage of the final product. What does impurity profile mean? It means we have to identify the chemical structure for some impurities parallel to their quantitative determination, either in API, active pharmaceutical ingredient, or in the finished product. Actually, this step is very important, especially if you want to register your product in local market or in the USA or Europe. You have to apply a complete file. This file should include all scientific and technical data. One of them is impurity profiling. Some impurities are very toxic, so identification of these impurities are important, parallel to Jordan, FDA, or USP, or British Pharmacopoeia, will get you to identify all the unknown impurities. Okay. As a special case, I will talk about the amsulfuride. This drug contains some organic function group. Here we have an amide, ether, amine, and sulfur. This drug has 8 known impurities, and according to the British Pharmacopoeia analysis, just you have to test 3 of these impurities. We have here 3 impurities with their retention time. Here we have at about 13 minutes the retention time of our drug, and each impurity has a specific its retention time. Our problem is, now we will talk in detail about our problem. Open storage, the final product, I mean absolute with its excipients. The company that I deal noted that there is an unknown impurity. It has a retention time about 24 minutes. And this impurity has a maximum limit, more than 0.1. It was about 1.5. So my work was how can I identify and structure oxidation of these impurities. All the periods, peaks, they are known. There is no problem with them. To identify the chemical structure of my unknown peak, I did force degradation study. Force degradation study means I have to induce the formation of the impurities by 2 routes. The first one, exposing the raw material against stress conditions, acidic, basic, oxidative, and thermal, and UV. Parallel to conduct some reaction between amyloid and each of the additive components. The method of analysis is based from the British Pharmacopoeia. It's based on reverse phase with mobile phase consisting of methanol and phosphate buffer. I'll talk about the results and discussion. The reaction of amyloid with each of the additive components didn't give the peak. I mean the peak at 24 minutes. It means the excipient has no role to induce the formation of this impurity. On the other hand, I did force degradation of the amyloid under stress conditions. For example, heating the raw material alone without excipients here, under heating with basic, alkaline media, acidic, in neutral, H2O2 with different concentration. In addition, I exposed the solid powder to the UV and to the heat. I found that none of these conditions induced my impurity, my degradant, except the degradation of the raw material under the acidic condition. So now we know the route. How can we induce and form our unknown? This sample was obtained from the reaction of amyloid with HCl. I got here a high peak of that impurity. Actually, I start with LCMS to identify the impurity. I did LCMS, but you did remember when I did LCMS, I have to replace the phosphate buffer in the mobile phase with the ammonium acetate. I have here, this is my peak at about 23 minutes, and here I have the retention time. The retention time was 216. So I know the molar mass of my unknown impurity. This is the advantage of LCMS. But this data is not enough. I have to do NMR. The next step, to get small quantity for NMR analysis, I did plate chromatography, and I obtained some quantity, about 7 milligrams of that impurity. Before I did the NMR analysis, I have to make sure that I have pure sample. Here, if you can note that this impurity, the isolate impurity, it's 100% area. It means it's high pool. So I can go further to the NMR analysis. I started with the proton NMR and the carbon. With the proton, I had these signals which is corresponding to that structure. No, I know now my chemical structure for that impurity. I have to go back to the drug. This is the chemical structure of the drug. The target impurity was this part: phenyl, O-methyl, amine, sulfone, and ethyl. Without this part of molecule. To confirm the data, I did the carbon NMR, and here you can find number of signal is equivalent and equal to number of carbon types, and did carbon NMR depth analysis. So now we identified this impurity. Without identification of this impurity, you can't register your product, even if you have all the other data. Finally, I proposed here the mechanism for the formation of this impurity. This is the drug. With reaction with H2O under acidic medium, the amide group will be hydrolyzed to give carboxylic acid. And this is normal. But in some cases, we have decarboxylation for the phenyl ring. And this part was decomposed to produce CO2. It means in the factory, they should avoid the reaction or exposing our drug to the acidic hydrolysis. Otherwise, they will get that.